Okay, so from the video that you watched about energy, you should have some basic understanding of some of the key concepts. We're just going to consolidate all of that now into this lesson. So the unit is called Work, Energy, and Power, and it's an extremely important unit because it ties into every field of science that you can think of in engineering and sports and everything. It is the universe. So one of the first things you can do is when you download this the handout, you basically see that there are some definitions. So it's really important to understand these material definitions. So the first one is matter, and matter is the stuff that the universe is made up of. I know it seems a bit ambiguous, but when you think about matter, it is physical things. Now, what gives matter mass and all that sort of stuff. We have to get into Higgs bosons and all this sort of advanced physics, and you can read up on that on your own if you wish. What is energy? Well, energy doesn't really have a substance. It is everywhere, and it's what drives things to happen, to move or to go. Right? It is like when you think about energy, it's like it's this energy that makes things happen. Okay, and again, a bit ambiguous, but they're difficult to sort of really quantify or not quantify. Sorry, to sort of come up with a definition. Now, the true definition of energy is basically that energy is defined as the ability to do work. This you must highlight. Okay, this is the definition of energy. It is the ability to do work. Okay. Now, basically, you require energy to do work on any object. Now, you've probably heard of a few things in the past, and when we talked about electricity and magnetism, or when we do talk about electricity and magnetism, we say that we realize that Faraday's law and Orsted's principle sort of showed, or they did show, that there was this connection between electricity and magnetism, and that electricity and magnetism are not separate entities. They're actually intertwined with one another. And what's neat about that is that it starts to give you this idea that, once we thought about electricity, once we thought about magnetism, we realize that they're one and the same. They're somehow intricately related to one another. You can move electricity through a wire to produce a magnetic field, or you can move magnets near wires and you can produce an electric current. Well, turns out that matter, when we say that matter is the material stuff of the universe and that energy has no real substance and it's what drives things to happen, or energy is defined as the ability to do work, we often think about matter and energy being two completely separate entities. Now, what we are going to learn in grade 12, and what you've most likely, everyone in the universe, maybe not the universe, but everyone on Earth has probably heard of this person here. German physicist around the time of World War II, was around in the late 1800s, and into the 1960s-ish. And Einstein basically came up with one of the most famous equations that most people don't really understand anything about, but he came up with this: E equals mc squared. And I think everybody realizes that that is a universal sort of equation that most people, maybe don't know a lot about, but they've heard of it before. Now, what is the E? Well, the E stands for energy. What is the M? The M stands for mass, and the C is the speed of light. The speed of light is approximately 3 times 10 to the 8 meters per second. 300 million meters per second. It's fast. Now, of course, there's a square on there. So this big number, 3 times 10 to the 8, is really 9 times 10 to the 16. Okay? So what this tells us, this equal sign is so important, because now this tells us that energy and matter, or energy and mass, are really the same thing. They're intricately connected to each other by the speed of light squared. So if you have 1 kilogram of mass, that's the equivalent to 1 kilogram times 9 times 10 to the 16. So that's 3 times 10 to the 8 squared. is that's 9 times 10 to the 16 joules of energy is contained within 1 kilogram of mass. So what that means is that mass is energy. It's a condensed form of energy. And energy is just a non-condensed form of mass. And they can go between each other. The most famous demonstrations of this are nuclear weapons. Nuclear weapons convert mass into energy, and a lot of energy. It's why they're so destructive. At the beginning of the universe, there was only energy. During this beginning explosion, this big bang, not really an explosion in space, but it was just this space-time sort of explosion. Energy existed, and it condensed into the matter that we have now today. It took all that vast amounts of energy divided by the speed of light squared gave us the finite amount of mass that we see sitting in the universe right now, on the earth, on you, everywhere. Originally, that was all just energy. So energy and matter, although we always think of them as being separate, are one and the same. They're just different versions of each other, and they can be converted in between or between each other. Another thing you'll learn in a grade 12 course, or if you continue on in science, is that another thing that we think of as separate is space and time. And you often think about space as being, the space around you, and time being this thing that flows, is this sort of time period. Turns out that space and time are the same thing. They're intricately stuck together. They're intertwined together, and there's something called space-time, and they affect each other, and they're warped and manipulated by other objects. Okay, so do some reading on E equals mc squared. There's a little more to this equation. It's actually E equals gamma mc squared, but the gamma factor in front of it is usually 1. And so this is what's known as the rest energy conversion. Okay, so, and again, you've probably heard of that, but didn't really know what it was. All right, so energy is defined as the ability to do work. Now, what is work? Well, it seems sort of circular here, but work is the process of transferring energy, and this is paramount for this unit. If I say that work is being done on an object, or you say, or someone says that work was being done, you are telling someone that the energy is transferring from one thing to another. Okay, you are transferring energy. If at any point in time you say that there is a transfer of energy, you have done work on the object or on the thing that you're talking about. This, we're going to come back to this a million times, because this is pivotal. It's so important to understand that work is the transfer of energy. In this course, we focus mainly on 2 types of mechanical energy. We're going to see that there are lots of other forms of energy, but we're going to focus on 2 types. We're going to talk about potential or stored energy, and we're going to talk about kinetic or moving energy. Now, potential energy, there are lots of different forms. There's something called gravitational potential energy. There is elastic potential energy, so the energy stored in elastics or in anything that's stretched or compressed. There's energy stored in gravitation, so you know that if you go into the top of a building, you have stored a lot of potential energy in you, right? Because you don't want to fall out of that building. Elastic potential energy, we know that this is what keeps us alive, chemical potential energy, because we realize that we need to unlock the chemical potential energy inside of food in order to give us energy and heat, and burning these sugars and carbohydrates and things like that in order to keep us moving and keep us alive. Kinetic energy, so there's in here, there's like atomic potential. There's just so many different types of potential energy that we could list here, and you can look them up if you want. Kinetic energy or moving energy, this is in the thing as well. This is the classical, like if you're moving at some speed, you're carrying energy with you. They both have the same units, but if I say the word potential, it means that it's stored, and if I say kinetic, it means it's moving. Okay, we'll get into more about that later when we talk about thermal energy and all that kind of stuff. All right, so the next thing. Well, let's take a look at the work and transfer of energy. All right, so the mathematical description of work. So what we're looking at here is that work is so the true mathematical formulation is that work is equal to the transfer of energy. So W is the work. It's measured in something called a joule. And the symbol for joule is just capital J. Okay. And delta E is the change or transfer of energy, also measured in joules. Now you're going to see below here that the joule is named after James Prescott Joule, late 1800s. He was a scientist who did a lot of work on the heat engine. So he actually did a lot of work on this relationship between work and heat, and sort of engines and all kinds of stuff, the internal combustion engine and things like that. So in general, now it says here, this is the true definition of the amount of work done on an object, okay? And the definition of a joule. So the joule is the amount of work done by an applied force of 1 Newton acting through a displacement of 1 meter in the same direction. That probably doesn't mean much, so we're going to come back up here and we're going to write down what it means. Work is the amount of work done by an applied force of 1 Newton to displace an object 1 meter. So the equation is, and this is just one part of the equation, there's a dot in between here. So the amount of work done is the force, and that's called the dot product. It's a vector multiplication of two vectors. We'll talk more about that later. It's more for calculus, vectors and calculus course, but nonetheless, we can talk about it here. So again, the force, this is 1 Newton. The displacement is a meter. So the units of work is a Newton meter. And we call a Newton meter a joule. So if you're talking about the amount of work done, a Newton meter of work is equivalent to a joule, 1 joule of energy. Okay, we're going to talk about this force times distance. So if you apply a force over some given distance, it tells you how much work is done. Okay, so down here, 1 joule equals 1 Newton times 1 meter. So it's the amount of work required to push an object 1 meter with a force of 1 Newton. Okay, that's it. Now let's see what we can do with that. All right, to add a little bit to this, there's an important point that we have to make about that equation that we just wrote down. The important point is that only the force component in the direction of motion does work on the object. And you're like, what are you talking about? Only in the force, like only in the direction of motion. Let's take a look at this guy that's carrying someone that's way too old to be inside of a cart, and he's pulling them down the street. Now, it's going to displace them 30 meters, and he's pulling with 50 newtons of force. But look, it's pulling on an angle. So here's the thing. Only the force component in the direction of motion does work on the object. So you can imagine that there's a force in this direction. Okay, so there's a force acting horizontally, which is the one that's displacing the object in that direction. And there's also a force pulling up, right? The force, there's part of this 50 Newton force is pulling this way. Part of the 50 Newton force is pulling up. the part that's pulling up is not causing this cart to move 30 meters at all. So it doesn't do any work. The component of the force that's pulling to the right is in the same direction as that displacement, and that's the force amount that does the work. So how much work is this person doing to displace this object that far? Okay, so we're going to do this two ways. We're going to look at the specific case, and then we're going to look at the general case. Okay, and you'll see it's very simple to do. So we're going to figure out what this is called: the force horizontal and force vertical. Okay, this is the hypotenuse. This is the angle. This is the what's called the adjacent, and this is called the opposite. I think that you can remember that from back in the day. So if that was 50, 30 degrees, we just have a right angle triangle. We can figure out this, and we can figure out that. So how do we write it? Well, we're looking only for, so the work done is the horizontal force times the displacement. Okay, so the horizontal force is, that's what we need to figure out. So that's this force here. Well, if we write down cosine of 30 degrees equals adjacent over hypotenuse. Well, the hypotenuse is 50. There we go. So if I multiply this across, I get 50 cosine of 30 degrees. Okay, and you're like, that's fine, I get that. And you just take out your calculator and you can figure out what that horizontal force is, or the force that's in the same direction as the displacement. And that's what we're doing. We want the force in the same direction as the displacement. And the answer is 43.3013 newtons of force. So 43.3 newtons of force is what's pulling this cart along this way. The vertical part is 50 sine 30. So 30 sine times 50, and it's 25. So 25 newtons is pulling up, but that's not pulling them in that horizontal direction, so it doesn't count. So how much work is done? Well, the work done is the force in the horizontal direction times the displacement in that direction, and we get 43.3013 times 30 meters will tell us how many Newton meters of force. So, sorry, how many Newton meters of energy or work. And it's 1,299 Newton meters, which is the exact same thing as 1,299 joules of energy. My pen is dying. There we go. Okay, now in general, let's take a look at what this looks like in general. You're gonna do the same thing. Like this. Now, I'm going to put an angle. Force horizontal over the applied force. Notice I'm just not putting in numbers. And I cross multiply, so it's F cos theta equals the horizontal force. And therefore, the work done was this times delta D. Substitute this in. F cos theta delta D. And how most people write it is this. And there you go. This will get you the same result is down here because we're just replacing F in cos theta, which we did here. And this will give you the same result of 1,299 joules. So this is what's called the scalar quantity of the work equation. Now, this equals F dot D. Now, don't worry about this part. These are vectors. This is called the dot product. This is a way to multiply two vectors. Multiplying vectors is a little bit different. It's quite a bit different than multiplying numbers, in specifically scalars, like things that don't have direction, because these two things have direction. That little dot and these vector signs takes direction into account. What this equation does is this in the form of a scalar, and this says just multiply the force times the displacement times the cosine of the angle between these two directions. And that will give you only the horizontal component, or the part of the force that's in the direction of the displacement. And that is extremely important. For most intents and purposes, if the displacement is in this direction and the force is in the same direction, what angle do they make to each other? 0 degrees. So if they're both pointing in the same direction, purely, like if you're pulling completely horizontally to the direction that you're moving, the angle is 0. And so your work is F delta D. And what's a cosine of 0? You put it in your calculator. If you don't know it offhand, you should know it right away. The cosine of 0 is 1. And so it's just 1, like that's it. It'd be cosine of 0, so just 1. What if the displacement is this way? Like a car's coming at you, and you're a super person, and you're able to push on it. Well, to stop it, well, if you're pushing on it, you're pushing on it backwards. And it's still going to move. The car's still going to move in this direction, but you're slowing it down. But you're pushing opposite to the direction of the displacement. What angle does that make? Well, that's 180 degrees. Well, if you put in cosine of 180, again, you shouldn't have to put this in your calculator, but if you did, cosine of 180 is -1. So you get negative work done. This is positive work. Nice little voice crack. Positive work, and this is negative work. There's a weird one. What if the two forces are like, let's say that you apply the car's coming at you, and instead of pushing against the car, you just start pulling up on the car or pushing down on the car. How much work are you doing on the car? The angle is 90 degrees. Well, what's the cosine of 90? Again, you shouldn't have to put this in your calculator, but if you did, the cosine of 90 is 0. 0 times anything is 0. And you get no work. Now, you're like, well, it still takes, I'm getting tired pulling up on the car. Sure, but you're not displacing it. So you're not doing any work on the object. And so whenever we're talking about work, what we're talking about is work being done on the specific object that you're talking about, not whether or not you're exerting energy and getting tired and all that sort of stuff. Okay, so what we're going to focus on next is those 3 zero work cases. Okay, so we're going to look at the 3 cases where 0 work is done on the object, and that's what we're going to really focus on. Okay, so what we're looking at now is what are called the 0 work cases. Now, when I say 0 work, these are cases where there is 0 joules of energy produced. Now, I put the line through it because in the past I used to just write 0, like OJ, and then people are like, "What's OJ?" And it's like orange juice. It doesn't make it like, so I don't know. It's ridiculous. Anyways, so the 3 0 work cases. Now, we're gonna look at case 1, case 2, and case 3, and we'll start with the simple one. So the key to start with is the equation. Well, this is the equation. All right. Remember, the cosine theta is important. And so what we're going to focus on now is, what if there, how is it that we could get work equal to 0 joules? Well, there's 3 variables, there's 3 cases. First one, you might just recognize, like just the force. Set it equal to 0. If there is no force acting on the object, then no matter how far it displaces, or the angle wouldn't even come into play here, but no matter how far it displaces itself, if there's no force acting on it, there is no work being done on the object. And so this is when the force applied is 0. You get no work done on the object. A lot of people are like, what? How does it even make sense? Well, this is what we call, and you can relate back to inertia. You can relate it back to inertia by saying, well, okay, if you take a paper airplane and you throw it, you've already applied the force. Once you've thrown it, there's no more force of applied force on the object, yet it keeps displacing itself. So you're no longer doing any work on the object, you in particular. Gravity is still doing work on the object because gravity is pulling down, and the airplane is going to drop over time. So gravity is doing work on the object, but you are not doing any work on the object. If you think about satellites that are in space, sorry, not satellites, spaceships that we've sent off to distant, outside of our solar system, once it's moving, there's no more forces applied. The powder, the nuclear power on the things have run out, but that thing will just keep moving. But there's no forces acting on it. And so there's no work being done on it. Same thing with asteroids that are floating around in space. Now, here's the thing. Asteroids that are floating around in space, they have gravity pulling on them still. So there is still some work being done by gravity. So the 0 work case of this type is difficult to find, but it is one way to get 0 work done on an object. And again, listen to the way I'm saying that. Work done on the object. And in case, like up here maybe, say, work done on the object. Like, that is such an important thing to remember, that we're talking about the work done on the object. I'm just going to keep saying that over and over until you're completely irritated by it. Work equals force times displacement cosine angle. Well, I think you're going to probably could have finished this lesson by yourself. Let's say the object doesn't displace itself. 0 times anything is, you get another OJ case. So force is applied, but no displacement. And you're like, what? How does that even make sense? Well, walk up to a wall, push a wall. You're applying a force to the wall. Does the wall displace? No. You are doing 0 work on the wall. Do you get tired? Yes, but we don't care about that. We're not talking about your muscles doing work. We're not talking about burning or exerting energy. We're talking about on you physically for pushing. What we're talking about is how much work is being done on the wall. If you walk up to a rock that's super heavy, or Thor's hammer, if you try and lift Thor's hammer, you can't lift Thor's hammer, right? Except for Thor. And if you're trying to pull, you can pull as hard as you want with as much force as you want, and you're going to be exhausted. But you were doing no work on the hammer at all. That is so important. Try and draw Thor holding the hammer. Last case. Okay, so the last case, you're like, well, okay, there's only one more thing left to look at, and that's this. Well, the only time that, one of the cases where cosine of some angle 0 is when theta equals 90 degrees. Then cosine of 90 degrees equals 0. And therefore, when that term drops to 0, you have an OJ case again. And so this happens when the force is perpendicular to the displacement, then no work is done on the object. You can think of like if you're carrying a tray or carrying a book around and you're pushing up on the book, gravity's pulling down on your hand from the books. You're walking around, um, and you might be displacing yourself in this direction here, carrying these books, right? You've got this book. Here's your hand. I don't know what that is. It's supposed to be a hand. Okay. Destroyed that. And you're pushing up on the books, but you're walking in that direction. You are doing no work on the book. If you change the elevation of the book, if you lift the book up or drop the book down, then you're displacing it vertically and the force is vertical. So therefore you're doing work. But if you are just walking around, you're not doing any work on the book, because theoretically, if we were not in a gravitational field and there was nothing else around and you stopped, that book would just keep moving in the same direction at the same speed and there'd be no work done on it. Now, if you change direction, you're now applying friction. And if you're applying friction, you're now applying a force in the direction of the displacement and you're going to get work being done. Same thing I said before, that if you lift it up, well, force, if you're pushing up and the force is up and you're displacing it up, you're now at a 0 degree situation and you're doing work. If you are pushing up, but you slowly drop your hand down, you're still pushing up on the book, but you're displacing it downward, you're doing negative work because the angle between the force and the displacement is 180 degrees and you're doing negative work. But if you're holding the books this way and you're walking this way, you're not doing any work on the books. Now, if you were to accelerate the book forward or slow down, yes, if you accelerate forward, then you're pushing the book forward in the direction of the displacement and there will be work done. If you try and stop, the frictional force is acting backwards. That's 180 degrees. You're doing negative work on the book to slow it down. So yes, if you're speeding up or slowing down or changing direction, there will be work. If you're lifting it up or pulling or dropping it down, work will be done because then the forces are in the same direction as the displacement. However, in the case where you're just walking in a nice straight line at constant speed, holding the book, the vertical force is perpendicular to the horizontal displacement and you get zero work being done. If you can understand that from what I just did, then you are way ahead of the game because that is a big thing to understand. Okay, let's take a look at some examples. And then you probably don't need me for these examples, but so if you want to try them on your own, hit pause, do them, and then come back to this, that would be great. And then you can just check your work. Okay. So a box is pushed along the ground with a constant speed with a force of 50 newtons. The box is pushed around a circle with a radius 10 meters. Sorry about that. 4 times. Calculate the amount of work done on the box. So work equals force delta D cosine of theta. If it doesn't tell you, typically we assume that theta equals 0 degrees. So F delta D cosine of 0 degrees, right, is 1. Cosine of 0 is 1. When you're doing these questions, put calculator in degree mode. I can't tell you how many of you, probably 50% of you are going to have it in radians by accident, and you're going to get all the wrong answers and not know why. And it's because you're going to forget to put your calculator into degree mode. All right, so that means that here the work is just force times displacement. Now, I just wrote way too many deltas. So now we think, okay, well, the force is what? The force is 50, but we don't know the displacement. So let's figure out the displacement. It says push along circle with a radius of 10 meters. Well, the circumference of a circle is the distance around the circle, and it's 2 pi r. And so the circumference is 2 pi r, so we just find the calculator, put in pi, and then if your calculator has pi, I'm just rounding mine to 3.14. So then we times it by 2, times it by 10, and I get 62.8 meters is the circumference, but we walked around 4 times. So the the circumference was that. Delta D was 4 times 62.8 meters. And that's 251.2 meters. So the amount of work that you would do, 12,560 Newton meters, which is a joule. Remember, a Newton meter equals a joule. That's how much work you would do in that case. Okay, wheelbarrow is pushed with a force of 98 newtons at an angle of 25 degrees to the horizontal over a distance of 20 meters. Calculate the work done on the wheelbarrow. This one doesn't even require hardly any work. No pun intended. 25 cosine, make sure you're in degrees, times 20 times 98, 1,776 joules. Now remember, that's because the wheelbarrow, which I don't know how to draw a wheelbarrow. So let's say that's the wheelbarrow and you're pushing it with 98 newtons and you're at 25 degrees. Then the horizontal force here, if you recall, is cosine, 25 cosine times 98, which is 88.818 newtons of force is acting in the direction of your displacement, which was 20 meters. So if you take 20 times 88.8, you get 1,776. Because that is the force that's in the same direction as the displacement. And that's what this formula does. That's how it breaks it apart. It doesn't care about this vertical part because we already realized that the vertical part is 0 joules of work because it's perpendicular to the direction of motion. Okay, another important example. There's a heavy cart rolling towards you. You're going to try and stop it. You apply a force of 140 newtons and it takes 7 meters to stop the cart. Calculate how much work you did on the cart. Okay. The cart's coming at you. It takes 7 meters displacement to stop it, but you are pushing in this direction to stop it, right? So if you're pushing in this direction and it goes, slows down, notice the force is opposite the displacement. So therefore you're having a negative acceleration, which will take it from whatever speed it was going to a stop. You use kinematics to figure all that out. This implies that the angle is 180 degrees. The angle between this and this is clearly 180 degrees because they're opposite to each other. Well, what does that look like? Well, that's force, which is 140. Displacement 7 meters, cosine of 180. Well, if you plug in cosine of 180, it's negative 1. So in this case, 140 times 7 and times negative 1 is negative 980 joules. So you do negative work on the object. Negative work on the object is a deceleration in this case, and you're causing the object to slow down. Okay, number 4. And again, if you're doing this on your own, you're just checking your work. That's great. 7,000 joules of work is done with a force of 45 newtons at this angle. Calculate the displacement. Okay, so you're just rearranging for displacement. And it's just work divided by F cos theta. So that's 7,000 joules of work times the force, which is 45, divided by cosine of 15 degrees. And hopefully you are putting everything in degrees instead of radians. And so we just get 7,000 divided by 45 divided by cos 15, displacement of about 161 meters. Okay. Now, this next one, you have a 15 kilogram object lifted with a constant speed, so no acceleration, from the ground to the desktop, which is 1.3 meters high. Calculate the work done. That means that you have a desktop like this. You've got a mass of 15 kilograms, right? You are pushing up on the force, on the object to overcome the weight of the object. Remember, the weight is mg, and you're displacing it in the upward direction. If you're going to move it at a constant speed, then these two forces must be balanced. So the force that you're overcoming, if you look at Newton's second law, F equals ma, if there's no acceleration, then the net force is zero, which means that the force you're pushing up must equal the gravitational force. So that would be mg delta d cosine of 0 degrees. Why is it zero? Because the force you're applying is in the same direction as the displacement. Cos of 0 is 1. So you get mg delta d. What we're going to learn later is that this, in fact, is the definition of gravitational potential energy, or the work done to lift an object in a gravitational field. So 1.3 times 9.8 times 15. The work done is 191 joules. So it takes 191 joules of energy to change the gravitational potential energy of an object from the ground up to, that's how much energy would be stored in that object if it was sitting on a tabletop at 1.3 meters. We're going to learn more about that later and do a very specific derivation of that equation. But for your understanding here, just realize that if you're not accelerating, then the upward force has to balance the gravitational force. Now, of course, at the very, very beginning, you had to accelerate it a little bit. Otherwise, it would never reach a constant speed, right? So you'd have to do some amount of acceleration. So this force would have to be bigger than gravity initially. But once you get it moving, inertia will carry it upwards. And as long as you keep the same force, it should just maintain that speed. Okay, an object is pushed at a constant speed along the ground with a force of 400 newtons at some angle. The object is pushed 12 meters for that much work. Calculate the angle. This question here, number 5, is going to become handy for some of your problems that you're going to be working on. Okay, so that's the equation. Now you're saying, well, I need to find out the angle. So what is the angle? So that means work divided by F delta D. It's cosine of theta. Now some of you are like, oh, well, what do I do here? How do I get theta? The inverse cos. Okay. And that's work over F delta D. So theta equals the inverse cos, and the work is 3,800 joules divided by the force, which is 400, divided by 12 meters, and you'll get your angle. Okay, so we go 3,800 divided by 400 divided by 12. So 3,800 divided by 400 divided by 12, and shift cos is 38 degrees. 37.6. About 38 degrees is the angle. Okay, so that's it. And what you're going to do now is the questions that I've outlined from the worksheet on the lesson sheet. So 12, 14, 15, it's listed on the website. Which questions you need to do from here. Do them on a separate sheet of paper on the back of this page and see how you can do with them. Okay, good luck, and we'll continue on with kinetic and potential energy in the next few days.